Welcome, everyone. It's very cool that you made it to the AI campus today for the monthly paper reading group of the Merantix Momentum. This month we have the research team of Merantix Momentum presenting their summary of the NeurIPS conference. We actually traveled to the NeurIPS conference, which was in New Orleans in the US. 1 or 2 weeks ago, and yeah, I'm very happy that today our researchers and engineers will present their highlights and their favorite papers. So we have Jonas, Alex, Julian, and Konstantin from Merantix Momentum, and we also have a special guest, Zach, who's an ML engineer at Vara, breast cancer screening startup. And yeah, just 2 sentences about Merantix Momentum. We are one venture within the Merantix Venture Studio, and we have basically 2 teams, 2 main tasks that we do. Like we have a consulting business that is helping the small and medium-sized enterprises to scale their machine learning solutions better. And then we also have a research team that is very forward-looking, and we try to really stay to the state of the art and see what's out there, and have the opportunity to look some years into the future and detect trends, and also create and gather knowledge that we can then use to inform our engineering decisions better. There are 2 logistical things that I wanted to mention. So one is that this meeting is recorded. We hope that everyone is fine with that. It will be uploaded to our YouTube channel afterwards. And yeah, if that's not fine for you, we can work it out somehow, I'm sure, and let's sit together. And then the other announcement is that you're very welcome to ask questions anytime. Feel free to just raise your hand, and then I'll pass you the mic, and you will need to probably wait like for 1 second or so until the mic picks up your voice, so just be prepared for that. But yeah, without further ado, I think we can get started. I would like to hand over to Jonas, who will present the intro slide on how we made it to NeurIPS, and talk a little bit about what we did there.
All right. Yeah, thanks everyone for coming. Super excited to be here and to see everyone. Also, specifically, it's in person again. I think it's like the number 3 or 4 by now that it's in person again. Before we were all online, so it's great to have these events in person again. To give you a little bit of a flavor about NeurIPS, like one of the things that is really exciting about these conferences is not only the scientific content, which is of course great, but also to get to know a lot of different people and to celebrate your team, and to actually experience like a full week of science nerdery. So these are just like a few impressions on there, and you see all of the different people eating po' boys, enjoying like the southern style of the United States, and also seeing like friendly researchers from Switzerland, from the HSG. But also what was really fun for us was to recognize that there was also a lot of different communities that we didn't expect. And if you think we went to NeurIPS, no, we actually went to Workboat. The conference center was so large that there was actually 2 conferences in there, and a completely different community that completely threw off the event for a certain time of period because people didn't know where to go to. And it's a very fun event. Actually, some people in the audience, I give you the challenge, like some people of the speakers actually figured out how to get a free pass to get in there. It's you're in charge to figure out who that was. With that being said, super excited to be here. Please ask questions. And I think the first speaker is Julian.
All right. Thank you, everyone. Yeah, I'm Julian. I'm a machine learning researcher, and I brought 2 papers on optimization. The first one is Greatest and the Ultimate Optimizer. Like this? All right. Yeah. Okay. Yeah, so 2 papers on optimization. The first one is Greatest and the Ultimate Optimizer. It's by Chandra et al. It's a paper that was out actually like already since 2019, so a long time ago. And they use a nice trick to tune the learning rate and other parameters of an optimizer, which I found really, really nice. Okay, so what's the general setting here? It's a general setting that anybody that uses neural networks is familiar with. You have a neural network, you have some data that you want to fit it to, and you have some setting in which you're working, for example, semantic segmentation, and you have some loss function. And the idea is now that you want to update your parameters somehow, and the most common way to do this is just using, for example, stochastic gradient descent or some variant thereof. For example, this would be the update rule for stochastic gradient descent. And the question is, how can we actually tune the learning rate such that we actually get optimal performance regardless of which one they got, such that we can actually get optimal performance in terms of generalization. And everybody in the room that trains the network is familiar with this one. But just to pick everybody out here. On the x-axis, we see the epochs. On the y-axis, we see the log. And there's 4 different choices of learning rate being shown here. And yeah, just to go through them, if we choose the learning rate very high, then we get, for example, the yellow curve up there. As you can see, the training diverge, also something probably everybody here is familiar with. If we lower it a little bit, then we might get the green curve. So it's the learning rate is still too high. You actually make some progress, but you kind of stuck, kind of bouncing on your local optimum. If you set the learning rate a little too low, then you might get the blue curve, and you don't really make any progress, and you might get stuck on a local optimum, and you don't really converge to something that you're actually looking for that gets you good generalization performance. So what you're looking for is the red one, and ideally you just have it from the start, or you'd find it in some automatic way. And this paper is actually proposing a way to do this that uses a nice trick from 2018. And the trick is about how to find the gradient of the learning rate. And this is how it's being done. So for this is the trick from Biden et al. From 2018. And the way that they compute the learning rate, the gradient of the learning rate, it starts like this. So you have the loss function, which is f, and your set of weights wi, and you want to compute this gradient. Then you first decompose it using the chain rule. As you're probably familiar with, you have the gradient of the loss with respect to the weights. So just the normal one that you used in SGD anyways. And then you on the right, you have the gradient of the weights with respect to the learning rate, which is something a little bit more complicated and maybe a little less intuitive what this could mean. And what Biden and I proposed in 2018 is just to unroll this a little bit. Hope you can all see this, yeah. So you just unroll this in terms of the optimization steps, and you just go one step into the past, and take the previous iterate of your weights, and just move one step into the past. And in this sense, you keep track of the previous gradient that you have over here. And you can, in this expression, then now you can actually compute the gradient of the learning rate, which ends up just being the dot product of the current gradient times the previous gradient -1. And it's a very simple trick. Biden et al. Only proposed to do this just one step into the past, but it generally works quite well. And what this paper is actually doing from this year's NeurIPS, so 4 years later, is to do this automatically. And the way that this is being done is by taking advantage of algorithmic differentiation. So you have the normal SGD step on the left, which is just exactly the step that we've just seen. But in your optimizer, you actually add this kind of small part of the computational graph that also updates the learning rate, which you can see over here. So instead of detaching your learning rate straight away, you add the learning rate like SGD step on the top. And this way, you in the end, you compute the exact same the exact same derivative as before, but you do so in a much more scalable way. Instead of having to manually compute the symbolic derivative, you can just do it automatically. And what's really nice about this is that this also scales to other parameters. For example, the exponential smoothing average that you compute in Atom, you can also just compute the derivative of this very easily, and it's in the same manner. And what this allows you to do is to be way less sensitive about these different parameters. Okay, so why would you do this? And the results they have some really cool results on this where they looked at how the choice of the initial learning rate differs in this case. So what's being shown here is 3 different plots with different initial learning rates. 10 to the minus 4, 2 times 10 to the minus 3 in the middle, and 10 to the minus 2 on the right. And what's cool here is that that the comparison to the baseline, where you just keep it fixed to the learning rate that's shown in the subplot, and the hyper optimization, like where you optimize it at each step, is that in the left, when you set your learning rate a little too low, then the hyper optimizer will actually recover this quite well, and you get a much better performance than the baseline. In the middle, if it's set actually to quite a good value, then you get a similar performance. And on the right, if it's set too high, then the baseline will be quite noisy. But the hyper optimizer will actually reduce this loss quite a bit, because it will, in a sense, decrease the learning rate quite a bit. So this is really cool because it makes it less sensitive towards the initial learning rate. And what they then propose is I guess the actual contribution of this paper, where they did something very funny. If we go back here, then what they did here is to add this additional kind of part to the computational graph, right? But what you can also do is just say, well, we can add this part to the computational graph, and then do a LCD step on the learning rate. But what you can also do then is to add an additional LCD step on the learning rate of the learning rate that you also added, and just keep on going in this way. Yes. It's pretty interesting, because what they showed in their experiments is that if you keep on doing then it becomes way less important what initial learning rate you actually choose, and you can recover from this much more quickly. And yeah, this is the general contribution of the paper, that the actual learning rate is not as important. Yeah. So just to conclude, so this it proposes a simple way to tune the learning rate in an automatic way. That stacking makes it much less important what initial learning rate you actually choose. And the unfortunate drawback is that this is very implementation dependent, and it, for example, it doesn't work for LSTMs at the moment. The second paper I also brought is also on optimization, but on multitask optimization. So what's the setting there? In multitask optimization, you have, for example, the following setting here. You have an input image that gets fed through some encoder, and then you have task-specific subnetworks that go through the different tasks. For example, you may have a semantic decoder to do seed segmentation. You have an instance decoder to identify different instances of the same object, and some depth decoder that predicts the molecular depth just from that one image. And what the problem that you're facing in the end is that you want to train this jointly. You want to maybe have different tasks take advantage of the other tasks from the additional signal that you get, but you don't want to have them conflicting. So there's lots of different algorithms to do this, to make it to find a good optimum that satisfies all the different tasks. A common way to train this is just to scalarize different tasks. So you have different weighting factors for the semantic decoder, instance decoder, and the depth decoder, for example, and you just add them all up, and you have your total loss, which you just use for backpropagation. Problem is now that you need to find the different weights, and finding the weights is very difficult. And similarly to the learning rate, you could spawn individual runs and just try out lots of different weightings of the loss function there. And in order not to do this, there have been other papers proposed multitask optimization algorithms, which find those automatically, also via AD or other different means to find these weights. But the problem with them is that they really have a major computational overhead. For example, if you look at one way you can do this is that you look at the different gradients that come into the encoder for each task individually, and then you find the gradients that make the weights of the encoder move into a similar direction, so that you have less conflicting gradients. And this paper just asks the general question: is this even useful? Do we need to make this distinction? or could we just like, is this necessary to compute, to make the, to add this additional computational overhead? And just to illustrate what the paper is actually asking here, if you take two tasks, could be, for example, the molecular depth estimation or like scene segmentation. You have task 1 and you have task 2, and you have the test loss there. And if we do like this static scalarization, where you just have 2 different weighting factors for each, and you weight, for example, task 1 a little more than task 2, you may get a point, for example, over there. So task 1 is reduced quite a bit in terms of the test loss, but task 2 is still quite high. Then you may change it a little bit, but keep it constant during training. And then you get that point, for example, and you get eventually, if you try out all these different weightings, then you may get a curve that looks like something like this. So what the paper is actually asking is, would it be possible if we change the weights during training to kind of break the boundary that we see there and find points that, for example, lay over here? And this would be ideal. And the question is, can we do this? Can we find this experimentally? If we fairly evaluate lots of different multitask optimization algorithms, which add this significant computational overhead. And what you see here is just one of their examples. They have a lot of different examples here. This is a language translation task going from English to Czech or French. And what you see here is unfortunately negative results, which is mainly what this paper is about. You see this blue curve, which is showing the static weighting. If you choose just 10 different values for each of the weightings for each of them for translation to French and Czech. And if these other algorithms were actually better, then we would see them in the lower left corner. But unfortunately, it's not the case. And that's their main result. The additional computational overhead that you invested in them, and unfortunately also the research that you invested in them, didn't really pay off as much as it would have liked to. Yeah, that's the conclusion. The funny thing actually is that next to this paper, there was another paper that showed the exact same thing. But they actually they didn't even look at the boundary. They only used a single weighting, just the constant weighting where you don't even, they call it unitary scalarization, where you don't even scale, you don't even change it there. But yeah, they showed the exact same thing. That was my contribution to optimization paper.
Yeah. Hi. I have one question to the first paper. Do you have an intuition why it shouldn't work with LSTMs? Or is that just an implementation?
It's an implementation detail, yeah. I think what they said in the paper is that PyTorch uses changes the computational graph of an LSTM within it's already in the implementation in the backward pass, so it doesn't work with their current implementation.
Okay, thanks.
It's just an implementation.
There was a very similar question in the chat. Please type your message in again or in a different way if this answer doesn't answer your question.
Okay. Thank you for the presentation. I have a question. So yeah, also in the first paper, I don't know if in the code it shows there's like a kappa. I guess it controls how how the alpha evolves as you train. Can you show the code again, like this code you have on
this one?
Before that.
This one?
Before, like just a code. That there. So there is this kappa. I guess so as alpha evolves, you have this parameter there. No?
You mean the kappa is the,
yes.
Yeah.
So is it not that, because I guess that's basically controlling how much alpha change as you train.
Yeah, that's the learning rate of alpha.
So it's not just pushing picking the parameter to a different place from the original alpha to this kappa, or how sensitive is this to the value of kappa? Like how close is the algorithm to the bigger selection of the value of kappa?
A good question. It's actually, that's one of the things that they are trying to address with this kind of stacking, because changing the kappa is exactly what they do. So they have an additional SCD step that just updates kappa and then the kappa 2 after that. But yeah, in that paper, they also show that it depends on what you choose there, but it's less dependent than just using the constant alpha.
Oh, because it's the same, like if kappa is too big, then you're going to have the same problems as the first graph. If it's too small, then you're going to update.
I mean, it's one of the tricks actually in that paper that the stacking is done in a way where each of the levels in the stack gets assigned a certain kind of learning rate to begin with, and then it starts updating. So the highest stack has a very high learning rate, and the lower ones just get lower ones. And this is how they actually make it work. I actually don't know the code, and I tried it. Yeah, it doesn't work otherwise if you just reverse the order.
Thank you.
Any more questions? Looks good. Okay, I think then we can go on with our next speaker. Thank you so much, Konstantin.
Yeah. Hi, everyone. I'm Konstantin. I'm a colleague of Julian, also machine learning researcher at Momentum. And I actually don't have two papers for you today, but my personal highlight of NeurIPS was a workshop called Self-Supervised Learning, Theory and Practice. And without further ado, you can see here the schedule. So it was quite a long workshop. And it had a total of 62 accepted papers, 8 invited talks, and it took almost 10 hours. And most importantly for me, it was recorded, and I could watch it online because I actually got COVID on the first day of the conference and stayed home the rest of the week. So with that, I want to go a bit more into the speakers. And you probably know a couple of these names. You definitely know a couple of their works. And the whole workshop, I would say, was of super high quality. And yeah, I personally never watched a full workshop of NeurIPS before and was quite surprised by the high-profile speakers that they attracted. You probably, if you have looked into self-supervised learning before, you probably know about Dino, you might know about CycleGun, and all of these people currently work on something related to self-supervised learning. That's definitely a focus of the industry or the field. And one thing that stuck out to me is was one of the talks by Mathilde Caron. Hope I pronounced that correctly. She's the co-author of Dino, SWAF, and Deep Cluster. And she talked a bit about non-contrastive self-supervised learning methods, and also talked a bit about her current work, just called Location-Aware Self-Supervised Transformers. And if you see this picture on the right here, it's actually an older idea. So I think like 3 to 4 years, about pre-training vision transformers with this jigsaw puzzle method. But she's using it in a way that the transformer is then trained on location-specific features, and that works to pre-train semantic segmentation methods. So most of the self-supervised learning methods so far are location-aware, but this method seems to yield quite nice results for semantic segmentation, which is of course always like quite heavy on labeling because you have to annotate pixel-wise. So that was quite a nice talk. Second one is from Jean-Baptiste Alaï-Rak. He's one of the co-authors of Perceive.io, variant of transformers that's designed in a way that it can be applied to multiple modalities. And he talked about Flamingo, which is his current work at or one of his current works at DeepMind. It's a vision and text transformer. So it's a model that can take in images or videos and text. Yeah, maybe the interesting part about it is that you can talk to it similarly as you would talk to ChatGPT. So you can give it prompts in the form of images and text, and then it will continue that prompt. So if you see here on the bottom, this is a very cute dog, and then a picture of a cat, this is, and then it will continue a very serious cat. So it's quite a powerful model combining two modalities, also using the perceiver architecture. So super interesting what you can do without labels in this field. The third part I want to talk about is a talk by Michael Owley. He's one of the co-authors of Wave2Vec, and about, I think, 2 years ago introduced Data2Vec. And he held a talk about general and efficient self-supervised learning, which we will go into more detail now. He's working at Meta.ai, so I didn't put the affiliations next to the speakers, but there was quite a lot of content from Meta. I don't know exactly, but guessing from what they do, probably also from the group of Jan LeCun. So he discussed two shortcomings of current self-supervised learning methods. One is that most of the algorithms are modality specific. So in the space of text, you have large language models, or in the space of vision, you have contrastive methods like SimClear or Bio. And you can theoretically apply either a method in some way to the other modality, but they tend to not work as well. And efficiency is also not really a focus. So usually only the results are reported, but it's quite costly to train or to use these self-supervised learning methods at the moment. And as I already said, he has a prior work called Data2Vec, where they focused on fixing the first issue, so modality-specific algorithms, and this Data2Vec method is capable of defining a single objective for vision, speech, and text. And let me introduce it shortly. So the idea is quite simple. You have images, and there as an augmentation, you would crop out part of the images. If you have speech, you just crop out part of the speech, and you would do the same with language. So masking out individual words, for example. And then the training objective introduces a teacher model, a student model. The teacher sees the whole input. The student only sees the mask out input. And then the student is trained to recreate the outputs of the teacher model. And with that, you generate your own training signal, and the teacher is basically lagging behind. So it's a copy of the student model that is lagging behind in the model weights. So that's the starting point, and now they try to introduce efficiency into this approach, because the problem here is that you basically need 2 forward passes for each sample in your training. And during NeurIPS, you already talked about this concept, Data2Vec 2.0. It's basically like an efficient version of Data2Vec 1.0, and I was quite surprised to see, okay, it actually only got published yesterday. So that's quite nice that you can find out about these cool concepts already 2 weeks in advance. So what is Data2Vec 2.0? And it looks really similar. You again have this masking out. But the difference is that you not only mask out one sample, but you actually choose a number of n random masks. So for each sample in your training, you have n masked versions. And then for each of these masked versions, you get a slightly different output from your student. And you train the student again to replicate the full output of the teacher. So instead of computing the forward pass 2 times for each sample, you computed n+1 times for n samples. So increasing the number of masks will also increase your efficiency. Yeah, so you basically reuse the output of the teacher model for multiple mask inputs. And what's quite interesting about it is that especially if your batch size is quite small, you benefit quite a lot from using multiple masks. So on the x-axis here, you see the amount of masks per input example, and y-axis is the final performance of the trained model. And this is, of course, nice if you have limited memory on your GPUs and cannot scale to, I don't know, compute clusters. They would be able at Meta, I guess, but it's nice to see their results with efficient methods. Yeah, just quickly see the results for different modalities. Here on the x-axis, you always see the training time in hours, and y-axis is the performance, one for vision. They compared, so blue line is always data to VEC 2.0, red line is data to VEC. And then for computer vision, they compared with mass autoencoder, for text with Roberta, and for speech with VEC, wave to VEC. And it's for each of the cases, it's quite more efficient. So yeah, my conclusions, it seems to be a simple, effective, and efficient, but general method. And yeah, putting the targets, so creating multiple mask versions and putting them into context with the teacher model seems to enable efficient training. And the limitation at this point is that while the method is general, the individual models that they use are still modality dependent. So they would use maybe a vision transformer or CNN for computer vision and a different type of model for text. And as I already talked about the perceiver a bit, that's data or modality independent method model, sorry. And yeah, Michael Howley also discussed that you could probably combine these two to basically receive a completely data and architecture independent, or sorry, modality and method, model and method independent of modality. Okay, too many words. All right, that's it from my side. Are there any questions?
We have a question from the chat. Does the student model have less parameters than the teacher model?
It's usually an exact replica of the student model. So, yeah, basically, yeah, you just have like an exponential moving average of your student model.
Okay, thanks. And does this also work if the masks are not stacked, like at random positions in a text or an image?
Masks are not stacked. I'm not sure how you would stack the model. So maybe this picture already explained it. The masks are always chosen randomly.
Yeah, okay, I think. Are there any questions from the room? Yes.
Thanks for the presentation. It's not 100% clear to me how you train the teacher. The teacher is just an exponential moving average of the student. that the case? Or
yeah. So what would be an analogy? So basically, the student it changes more rapidly, and you basically update it. Yeah, you slowly update the teacher.
oh, okay, yeah, I know what.
Yeah, sorry.
I was just not sure if that's the case. I think you said it like the last sentence or so. Thanks.
Yeah, as far as I know, it's just an exponential moving average. So it's quite similar to, I don't know, bio in that sense. Yeah.
Sorry, I don't know if I missed the opposite. What's the performance check down? Like, what are you, so it's converting the data into vector, and what are you checking the performance on?
Yeah, that's a good question. I skipped over the answer to that. So I'm not entirely sure what the references would be for speech and text, but in computer vision, you usually take the representations that you learn during the self-supervised training and then train like one linear layer, like as a classifier after the training. So then you take a small amount of label data and retrain the last layer. That could be an example. So I think that's what they did here.
Cool. I think we don't have any more questions from the room. Thank you again, Konstantin. And we're ready for Jonas.Cicero.
All right. Thank you. I want to talk a little bit about Cicero, which is actually a paper that was not necessarily associated with NeurIPS because it came out a little bit before NeurIPS, but they had actually a whole session on this system. And I'm super excited about it because it culminates a research agenda that Facebook followed for about like 3 years. And it shows essentially a capability that we didn't believe was possible about like 2 or 3 years ago. To just get started, you will notice I didn't put the author list on this. It's one of these big collaborations of 15 plus more people and 3 years of research. Essentially, the idea is to figure out how can you do a human language cooperative game. And it's based on the strategic game Diplomacy. I don't know if people know about it. It's essentially an online game where you negotiate on a one-on-one message with up to 6 other players and try to get to collaborate and conquer territory over some time. So I highlighted this paper, so it's like a lot of snapshots in here. To give you like a high level idea, the paper is fairly sparse, so I just mostly described the systems engineering here. And if you want to follow the research, it's probably going to be like about 10, 15 research papers deep. So the idea is here you have to cooperate and compete with each other. You have to coordinate with other players in your game. And it's a super interesting result since it's a multi-agent problem where you have cooperation and competition at the same time. So typically, if you think about like systems like Dota and other RL, you have always a team, you know where your teammates are, and you have the opposing team. So this is a different kind of multi-agent reinforcement learning setting, and it's super complicated. The other part why this is super interesting is because games that involve cooperation typically do not have like a simple Nash equilibrium. So if you think about like 2-player zero-sum games, they are adversarial, and you can actually prove that any kind of complicated reinforcement learning algorithms always converge at some point. Might be super inefficient, but it converges. However, these kind of guarantees we don't have in these kind of cooperative competition systems. So it's not even clear that you can efficiently converge onto a single strategy and solve this game at all. That's why many people believe this is actually not possible. So here, diplomacy gameplay, there's a little bit of a video here that highlights what's going to happen here. The challenges are that you need to understand people's motivations and perspectives. What are their incentives? You need to understand from these incentives and the current board game and the complex state, you need to understand what is your plan that you're going to follow and potentially adjust your strategy. And in the end, which makes it really hard for an AI system, you need to express this in natural language. and not be detected, because otherwise you would definitely see like you're a bot and people would line up against you. So it's kind of an interesting version of a simpler Turing test. So I find this super fascinating that this worked. And yeah, let's go through this a little bit. So here's a systems overview of what's happening, and we'll break this down step by step. Essentially, it's a coupling between a reinforcement learning algorithm and a natural language message generation system. They call it the dialogue part and the strategic reasoning part. In the dialogue system, you try to figure out, all right, there's the, I'll just tell you what is written here. Essentially, what you're trying to figure out is that you're trying to model intents and actions of other games and of the people that are messaging you. So you have to take the message that's coming in. You need to figure out what is the intent that the person expresses, and based on that, differ some actions and do some essentially initial language understanding. The other part is that you need to figure out, based on the action state, what is the intent and the strategies of the other players in conjunction with this kind of system, because you can only see the dialogue with you and the direct message that you have on top of that. That's the strategic reasoning part. Then there's the dialogue system that you need to take this from you need to get the strategic reasoning and these intents from the messages directly. So this is the lower part. How do you get this out and build this? And the third part is then essentially just like a simple message filtering. That is a trivia part in the system, but nevertheless quite important, because they essentially know that the AI is not good enough in terms of initial languages. And before they send it out, they actually have a classifier and a filter to make sure that the AI looks like a human. So that's, for me, important caveat, so that they still do that, and which is the case for many open-ended text problems. So let's break this down. And here's where the paper becomes interesting, because they focus a lot on the dialogue system and leave the strategic reasoning part a little bit out, which I find unfortunate, because that's actually one of the core functionalities, and I'm not quite sure why they did that. So dialogue system. First, what they need to figure out is like, you want to marry the reinforcement learning part with the messaging part. So what they figured out is like, if my agent has a strategy, how do I convert that strategy, that action space of my reinforcement learning part, into a message? The idea is simple. You want to actually do intent conditional natural language processing, which we already know quite simple how to do it. You condition a transformer with a few tokens, you generate a text, and that's it. Now, the hard part actually becomes, how do you create the data set for doing so, for training that? And here's the interesting part, how they do it. They measure something about past history. So they scrape the big data set from a public server, which they did in conjunction with the people running the server, and figured out that whatever is being said in a message is actually the true intent. So they look for messages that are closely related to what is happening next on a strategic board, and just label this is a true intent, which is actually kind of a little bit of a shortcoming, which I found very interesting. So it seems that if they do it and model it in this way, the model cannot actually measure or figure out betrayal. That's kind of a shortcoming, and they never really mention it in the system. They say like, yeah, the message is not honest, we cannot do this really, and so we say this is truthful and just sweep it under the rug, and there's not much debate on this. And somehow, somewhere in the paper, they mention, yeah, by the way, we anyways don't want to do this because the reinforcement learning algorithms takes care of that, but they don't have actually any proof for that. So keep that in mind. The second part, once they actually have that part, they now start to train they use that intent model to actually extract the intent, and then use that to label the data set itself with the annotations. So they bootstrap an algorithm to actually extract the annotation and create a data set with the labels for new systems. And then finally put this whole thing together, right? Like they have now a labeled data set. They use that data set to train a dialogue model. simple on like they use a text-to-text model based on a specific type of sequence model. In this case, it was a, what was the details, a BART-based R2C2 model, seek-to-seek model, used that labeled data set and essentially trained a dialogue system. And now they essentially have a system where they can say, if my reinforcement learning algorithm gives me a specific type of intention and strategy that I want to have out, they can turn these action pairs into a dialogue system. Yeah, that is one of the major parts. And the reason why they have to do it in this way is that if they wouldn't use an RL state system, they could never go beyond imitating humans, because you can only be as good as the data that you have. So you need to figure something else out to actually go beyond that. And that is the strategic reasoning part from the reinforcement learning algorithm. So finally, how do they connect all of the dots? So here's the final inference model. They essentially replace the intent model with the planning module, which I'm going to talk about in a second. They use the planning model in order to get the conditioning parts of the language generation, put it into the dialogue model, create a message, and send it over. So that's the lower part of that problem, which I personally already find quite interesting, because like it took a lot of steps to actually get this right. So for me, it's unclear how transferable this is to other kind of systems, because you do a lot of assumptions in there, and it's definitely not an automated fashion where you can just push a button and this will simply work. So now to the reasoning and planning engine, and that's where it also become interesting for me, because they just like stopped talking about like the details of this thing and just like said like, hey, we did this kind of algorithms and did a bunch of equations, and that's about it. So one of the things that for me was very fascinating is that they essentially not only model the own agent, but they have several agents in the reinforcement learning algorithm that simultaneously models the policies of every single player in there. And that is within like a single reinforcement learning algorithm. So you essentially have like an agent who's not only figuring out his own strategy, but also tries to learn about the strategy of everybody else at the same time. And they do this so by looking into holistically at the whole state and take into account the whole messages and all intents that they had individually with each individual player. And from that, try to infer the intentions and systems of the other players. And here is kind of where it gets murky, because they say like by doing so and looking at like what actions happen after, they can essentially identify betrayal, which may or may not be true, because like the messaging and the intent module is a little bit off on that one. They also use a specific type of behavioral cloning algorithm. Behavioral cloning is like a simple baseline if you want to mimic human behavior. They use something that is called Pickle, which is a regularized version of behavioral cloning in order to actually get the system running, and then reiterate this with a little bit of self-play after the fact. They then go in and say we're so here's the part about the deceptive measures. They say like they don't model the deception directly, but we rely on Pickle to directly predict the policy for other players, and so they claim that this then takes care of this. We already talked about this. The problem here is like that's my flag. They have two algorithms. This is called Bill Pickle and Pickle. Super sparse in the paper. We don't know what's happening there. It's a behavior cloning algorithm, and the rollout to see like what is the best policy under the assumption that several players are playing at the same time. And that's where it gets also interesting, because like, that is the key component here, which we don't know, is there is no convergence of this problem, which I told you in the beginning, like it's a cooperative competition game. And here they have to actually solve that problem in there, because you have to do several rollouts depending on your state and your action. The state of the other agents change, and you have to find the optimal policies under several different types of rollouts. And they just completely don't talk about this. And it's also unclear how at that point, because the dialogue model and the reinforcement planning module are starting to converge, because you might want to deceive someone, but your intent model actually doesn't allow for that. It's also unclear how they actually brought it in and said like, yeah, it's a problem, and somehow it worked. And they don't tell you how they actually did that. Conclusions. They played with Cicero in the online game. It ranked top 10% of every single player that played more than like 2 or more games. It also had like a bunch of other impressive scores. There's a little bit of a game how they show for coordination and negotiation. So the paper itself is actually worthwhile reading. Go in and look at it. It's very accessible, at least at its high level. If you really want to dig into the details, you will be frustrated. My conclusions to take away from this is it's a really, really cool work. And you can see like how 3 years of work really culminated in that. It's very sparse on the details, despite like having like a 30-page supplementary material. Yeah, thank you, science journals. It's in that case really hypey, and that's how it got in there. At least they have the code released, which I find super cool. You can go in and read all the details about that part. Hopefully they didn't spare anything out. And finally, the data set and the preparation of the data set they have not released, which makes it really hard to reproduce and figure out what actually goes on in the data set and whether changes to the data set will change the outcome on that. With that being said, thank you. And yeah, maybe there are questions.
I just saw a question in the chat. What would be the practical use of Cicero in your opinion?
What is the practical use? It's a good question. I think for me, it just like is mostly interesting because it's an update of my belief what AI can do. Right now, I think a practical application is not in sight. However, if you think about public deception capabilities, that moved my needle on that system, because you now have essentially an agent that can mimic these kind of behaviors, and the capability is ready, essentially. Maybe there's still like a little bit of an artificial game there, but like thinking about like the fact that you have an established goalpost now, and then think about like 2 or 3 years into the future, that is at least like a technological update, and that's why I think it's significant. I wouldn't say there's like a concrete application that I have in mind at this moment. Maybe some of you in the audience have one, but for me, it's like just simply very good science and a really cool demonstration. Wish there would be more details on it.
Anyone else? I was wondering, like this reinforcement learning module that's used for planning and the language model, are they somehow jointly trained, or I was a bit like uncertain about that?
I highly doubt it. I don't think there's a simple end-to-end system, which you can see by the fact how they actually built like their data set to begin with, right? They made some assumptions to how to train an intent model. That's the first model that they need to train. Then they use that intent model to actually label the data set that they train on for the intent model. Then they take that model in order to train a dialogue model end to end, right? Because like now you can simply take any kind of intentions and strategies and put it into the dialogue model. And then the murkiness becomes because they just, instead of the intent model, they just put a planning module in there. And now we are stuck with like, how do they train the actual planning module, except that it's like a dill pickle model on the full state, taking into account like the extracted intents and state action pairs. So I don't see how you can actually train this end to end. I have no idea how they would make the gradients flow all the way through like to the dialogue model. And on top of that, you actually have to be as good initially so to fool human players, right? Like otherwise you essentially run into the problem like you have to have like thousands of players that are willing to play with a very, very dumb AI because it really does like some stupid stuff, and you cannot train it in self-play. That's like one of the key points, which is like a difference to Dota. You cannot train these models in self-play.
Thanks. Any other questions? Otherwise, we move on to the next speaker. Not sure who's up. Yes. Cool. Awesome. Thank you.
Okay. Hi, online crowd. I'm Alex. I also work at Merantix Momentum in the research team, and I'm gonna start with talking a bit about the forward algorithm. In case you're active on Twitter or LinkedIn, you might have encountered it already. So in my feeds, I already found like a couple of posts that read something like backpropagation is dead. So that was like in reference to this talk, which is not true, just to put it first. But yeah, so for context, so Geoffrey Hinton was invited to give like one of the bigger invited talks. Because it was the 10th anniversary of AlexNet this year. And in the course of this talk that he gave, I think it was like 45 minutes or something, he presented a little something about what he has been working on lately. It's yet really published. I think on the website of the University of Toronto, he did publish a paper about it, but it's not really a real paper yet. So it looks a bit like this. So preliminary investigation. Not all the details are clear yet. Just so to keep you a bit up to date, I'm gonna. So since it's Geoffrey Hinton, it's not really a big surprise that the motivation comes from the field of neuroscience. So basically, he's saying in this preliminary paper that it's very unlikely that the brain learns from backpropagation. So he gives some reasons for that. So for one thing, there's no derivatives in our cortex, and nothing is stored in the way that humans learn. So it's not like we keep track of our gradients and then backpropagate through them. And then also we learn from a stream of continuous data that happens while we still process, we already learn. That is like really broken down. I'm not a neuroscience, but roughly that's how the argumentation goes there. And so based on this, he proposes basically a new way to update model weights, which is called the forward algorithm. And so in this whole paper, there are like not many graphics, I think one. So I found this really nice thread on Twitter for you who made these really nice graphics basically of it. So always better for a presentation. So this is a regular case of training a neural network, as we all know and love it. So we do like forward pass, then we like through all of our layers, then we compute the loss function on our outcome basically, and then we backpropagate what we've learned like through the layers. And so now for the forward algorithm, it goes a little bit different. So basically we do have two concepts in the paper, and they're called good and bad data, or positive and negative data. So basically I'm going to go with this example. So this could look differently, but like this is one example that he gives in this paper. So he tries this out with MS first, and basically you have as inputs these MS images, and the first 10 pixels, they are usually always black. So they now contain the class label, so to say, of your respective number that is depicted in the image. And then the good positive examples have like the right class labels, and the wrong samples have the wrong class label. And now, so what happens now is, so basically the biggest difference is we don't have a loss that we backpropagate, and instead we optimize each layer on its own. So every layer has basically its own objective function. So we still learn from a loss, so to say, but we compute that loss for every layer. So we only have one derivative. We don't have deep chain rule anymore, and like we don't backpropagate through each layer. And Hinton calls this like the goodness function. Yeah, the papers. Yeah, it's work in progress, I think. So he calls it the goodness function, and it's basically optimized per layer. In his paper, he just uses the sum of squared activation. So that's just what you can think of now. But it doesn't necessarily have to be that in the future. So basically, what this now does is we give like a positive sample, and then we just want our individual layer activations to be as big as possible for a good sample in each layer, and to be as low as possible for a bad sample, so to say. Here illustrated with these emojis. Yeah. So this is basically what we train for. So we don't have, like we would have in the supervised case, where we do backpropagation, like an output layer that has like a softmax on it, and so on and on. So one important thing about this is actually you have to normalize these layers in between, because otherwise it's quite trivial to train a following layer, so to say. Like if you think about it, like if the activations in this layer would already be super high, then it's kind of trivial for the follow-up layer to identify whether or not the first layer thinks this is a positive sample or a negative one. So they are normalized between the layers. Yeah, so this is roughly the idea that he sketches out. So, yeah, he goes a bit further than that, but yeah, just for you to imagine, like, there's no code published with this paper together. So there are some people who try to implement this online, but the paper is also a bit like low on the details. So I think it's for here like more about like a general intuition of what he's working on. So basically in his paper, he says we can think of using this for contrastive pre-trainings of a network. So the example that he uses would be here in figure 1. So we create bad examples by using like a random mask on MNIST images, and then we get this hybrid image that we can use as like the bad data, and then the good data is actual MNIST images. Then he also argues that the algorithm has the advantage of that we can use it in an alternative to reinforcement learning methods, since we don't have to backpropagate something to the network. Like if you think about it, if we have like a black box in the middle of our neural network, that actually doesn't matter if we can't backpropagate through it. So he also sees this as like a possible alternative to some reinforcement learning methods, like, yeah, think about reinforce or yeah, other non-differentiable operations that you could use. Yeah, and then there's also a small section where he argues that this type of optimization is very power efficient for certain pursuits. Yeah, I'm not an expert on electronics, but yeah, if you're interested in that, I would refer you to that. And he also goes a bit about like to branch this a bit out into like a recurrent-ish version of this paradigm, basically. So there the objective is to match always to the above layer. And put the same image as input in the layer input into the network multiple times, and then by only updating to the forward layer, so to say, or to the agreement to the forward layer, you get something like backpropagation. But he's very vague on this in the paper. And yeah, there are also not a lot of details on like how this is implemented within there. So he evaluates the performance of this recurrent-ish version. Also on Cypher 10, it behaves a little bit worse than regular backpropagation. Yeah, so in case you encounter one of these very hyped up articles about it, maybe just to keep in mind that this is like really work in progress, and this is like a passage from the paper itself. So he does say himself that it doesn't generalize as well on several of the problems that he investigated, and it's unlikely to replace backpropagation. For applications where power is not an issue. So here he revisits this part on this being very efficient to implement on certain circuits. Yeah, and maybe think of it more as like not superior to backpropagation, but more of a better model of how our brain actually works in the form of a neural network for now. I think someone posted to the chat.
Yeah, there are some questions. I'll pick out one. So are you computing the error on every layer or every node? Like,
yeah.
What does this loss function look like?
So basically, you would have a loss function for each layer. And so this layer, for example, only optimizes that, like for good samples, these activations, the squared sum of these activations is pi. And this layer only optimizes, like has the same objective, but only for these activations. So every layer is trained with a, like just imagine like there's a loss here, then there's a loss here. So each layer has their own loss. That's the difference. You don't have one loss that you backpropagate through the whole network.
Yeah, thank you. Are there any questions from the audience? Thanks for keeping up online. Very active crowd. Thanks.
Okay. So how would you actually make a prediction? Because
Good question. I should have touched on that. So one idea is that you could use this for like a pre-training with this proxy task, so to say. And then you would expect that these weights look identifiable, so to say. And you could train like a linear classifier layer on top of them, like freeze them. And the other option would be to just try this, like imagine you would have this input, like a 7, and you just insert it 10 times with 10 different labels and see, like sum up all activations in the network and then see to which label the network responds most. So within this paper, he actually like tried both of that out, and the second one with just passing it 10 times works much better. Obviously, like this is how the network is trained. So yeah, that's definitely interesting, but the slower version, the better one.
And basically in the output layer, you have like one neuron saying good or bad, and or do you average all the predictions, or?
You don't have an output layer because you don't have this notion of like your last layer being expressive for the outcome for the whole network, you know? Mm-hmm. I mean, in a sense you do, but it's not like as interpretable as if you would train this directly. And you don't have like this, if you think about it, like this intuition of like the last layer summarizing up the earlier layers necessarily. Like it depends on how your training data looks like. There are some quite like tweaks that he also mentions in this paper of making this classification in still working. Yeah, and for basically enforcing this hierarchical structure through the design of the network. Like, for example, he makes some experiments with only allowing certain amounts of connections in these layers, and then you have something that resembles like the perceptive field in CNNs or something like this. But by design of this algorithm, that's not necessarily a given. And then it's also not that likely that the network necessarily goes to learn this by itself, since the task is not directly given.
Thanks.
Awesome, very interesting paper. Thank you. One more question. I was okay. Sorry, you were just clapping. Oh yeah.
Hi, and thanks for the talk. So would you always need good and bad data to train this?
Yeah, in the paper they mention it, like, I personally thought of it a bit as like a contrastive approach, because like if you think about it, you only have good data, then your network just scales up the way to have like huge activations for any input you give. So you don't really have any incentive to not go into this mode collapse where you just have like huge activations. So I would think you need both. Yeah.
It seems really interesting to me, like especially with the motivation of like the neurological background, and you're looking at the human brain. This kind of approach is first imposes that we always learn from good and bad data. We need both, which I think is probably unlikely for humans, especially if we already have gathered some information. So maybe have a pre-trained version of the network. We could probably learn from a few positive examples quite quickly. And also, like, it seems like a lot of redundancy even after normalization. You would still have a lot of correlation between the layers. Seems still probably quite redundant, but it's an interesting idea. But yeah.
Yeah. I have a similar opinion about it. Yeah. Or a feeling, but like maybe we all just don't get it yet. Okay. And if there are no more questions, I'm going to talk a tiny bit about another workshop that I really enjoyed, which was the transfer learning for natural language processing workshop. The paper that Johannes presented earlier was actually also from this workshop, so kind of stole my thunder a bit. But, no. Yeah. No, I didn't want to say that. So no, I've been recently quite fascinated with these adapter structures, and there were like two quite interesting papers that touched upon it, and I thought maybe this is also interesting for you. Just to recap on what adapters are. So basically, as you probably all know, in natural language processing, there are a lot of approaches to work with pre-trained models, and usually you have like a pre-trained language model and you fine-tune it for your downstream task. And adapters are basically an alternative method for doing transfer learning with big pre-trained models. And the rough approach is, instead of fine-tuning all of the weights in your pre-trained model, you instead freeze all of the weights and you just put in some additional layers in between that you make trainable. And the good thing about this is, like, this is a much smaller number of parameters to train, so it's much less costly. And at the same time, there are a couple of papers that show that you can actually keep a similar performance to full fine-tuning. And then if you think about it, like, you have one pre-trained frozen model that you don't change, and you only put in some trainable units in between and fine-tune it on a task, and you do that for multiple different tasks, then you can actually use one bigger model with a set of different adapters and then use it for multiple tasks by only switching out the adapters, which might be beneficial in case you deploy this model someplace, or I'm sure you can come up with some scenarios. And then, the most widely used adaptive structure, just to give you like a bit of an example, like, so here to the left, you see like a regular transformer layer. So we have, actually don't see this on the screen. We do have the multi-head attention followed by some feed-forward layers. And before this layer normalization layer, we insert the adapter, and then the adapter layer looks like this. So basically, it's like a down projection and a non-linearity and an up projection. So since typically this down projected dimensionality is chosen quite small, this does not add like a lot of parameters to your network. So typically it's like 2% of like all of the model parameters that you add in. And that you then actually train, so it's much faster also. Okay, so this is like the setting that we had. And then the interesting paper that I wanted to show you is basically a mixture of expert model with adapters. So the idea is you start with a set of adapters that you have trained already. And then they introduce this additional layer on top of the set, which is called AdapterFusion. So basically what you do is that you learn attention weighting between these different adapter outputs. And it looks a bit like attention. So these adapter outputs are interpreted as like value and key of this supposed attention, and the input to the adapter is interpreted as a query, and then the model looks like this. So basically you can learn how to best combine the outputs of your adapters. And so in this setting, the adapters are also frozen. So the whole network is frozen. At each layer, we have these adapters. They are also frozen. And this is the part that's trained, like the AdapterFusion model. So maybe to also say this before the next slide, one goal of this paper is basically to investigate like how modular are adapters, like how much can we see them as like one single module for one task. And the experiment that they thought of here is basically they take 16 adapters that they trained on different tasks. And then they train the AdapterFusion model on the exact same 16 tasks, and then basically investigate, will the model select its own adapters that we fine-tune. So, and this is what you can see here actually in this picture. So there are different, so now we are at the point where we already trained the AdapterFusion, and we look at how the different layers mix the adapters per task. And it's actually quite interesting. So you can see that for a lot of the tasks, the model actually does choose its own adapters purely, and none of the others. But there are some tasks for which this is different, and it's quite interesting. For example, if you look at the CB task here, I forgot what it's short for, but this is a entailment task. So you have two sentences and you predict does one sentence logically follows to the other sentence. And as you can see, for example, here in layer 7, it does make use of the multi-NLE adapter. And multi-NLE is also an entailment task, so this makes sense at first sight. And it also makes use of here in layer 9 of the argument adapter. Argument is a semantic similarity task, so kind of related task. So basically they investigate these type of things are a bit of on a higher scale. And there's a really interesting trend. So what they basically find is, maybe staying with the example, like CB is a really low resource task. So it has, I think, less than 10K samples. Then, for example, Min.E, which was the adapter that this task used a lot, is a really high resource. I think it's like 400K or more samples. So in general, they found this trend of low resource tasks using adapters of more higher resource tasks, and then also being able to achieve quite a significant gain in performance while doing so, which is quite interesting, I think, and kind of shows that adapters do have this type of modular nature, that they are quite descriptive for their respective task. Yeah. And based on that, they motivated another really interesting paper, which is the last one I'm going to talk about. It's called MedX, and the idea there basically is then to utilize these adapters to do cross-lingual transfer. And yeah, so basically the starting point for this is there are a lot of multilingual models out there, like a multilingual bird or M-bird, and they typically suffer from something called the curse of multilinguality, which basically means if you train this network on a multitude of languages, then the more languages you add to that, the more performance deterioration you're going to witness, which intuitively, I guess, also makes sense. And this is especially the case for languages that are low resource, and the model has seen only occasionally. And here, so the idea of this paper is basically 3 steps. So first, we train language adapters, what they call. So we add adapter weights, and then we just fine-tune our model again, the multilingual model, for mass language modeling. So this is the typical pre-training task for language models, and just adapt our adapters, not intended, to the language. And we do this for high resource languages like English, but also for very low resource languages. Here they choose Quechua as an example, which is a language that multilingual bird has never seen before. So we do fine-tune the model or fine-tune these adapters, language specifically. Then we take the high resource language, which in this case is English, and they fix the language adapter they trained before, and add another adapter on top of that. And then they train the network again. So only the adapter is trainable, the rest remains fixed, including this language adapter. And they train this for a specific task. In this case, it's it's entity recognition. So we take this task adapter, this NER adapter here, and train it on like the source language. Okay, and when we're done with that, we keep the task adapter, but use a different language adapter of the low resource language. And then they use this network to do named entity recognition on Quechua language. Yeah, cool idea, very efficient also in training. Yeah, so basically they did like a quite extensive evaluation of this approach. So they divided these languages in languages that multilingual bird has seen before, languages that it has not seen, but it knows the script. So the underlying rules, so to say, of the language, like from other languages that are maybe related. And then they also tried this out with languages where that are really small or belong to their own script, basically. So you can't really deduct rules from other languages that you know. Yeah, as expected, like this only really improves in performance when the script is known to a multilingual bird. Yeah, the reason for that is probably here in the percent of the unknown tokens that you can see below, like which makes sense. So yeah, since these languages are so far away from what multilingual bird is used to, but yeah, I think it was quite an interesting idea, and might also be applicable to different problems. Yeah, that was my highlights.
Thank you. One question from the audience or not? Yeah.
You talked about training or basically fixing the layers in the AdapterFusion, but then training this AdapterFusion attention module. Do you know what they do with the layer norms? Because these are usually also task dependent in adapters.
I think they train them. They always adapt them, I think. So the norm typically follows, right? Let's see. Yeah, it's typically like the following layer. So I think I had the same question, and they keep tuning the norm. Retuning.
So I was referring to the AdapterFusion paper.
Oh, there actually, I don't know. I didn't look at them. Which,
okay.
Yeah, sorry.
No worries. Thanks.
Okay.
Cool. Thank you so much. I think then we'll move on to our special guest. Thank you so much. I think we will switch mics. I'm very sorry for the loudspeaker. It seems to have strange noises every now and then. Yeah, thanks, Alex. Yeah, I will give it.
Thank you, Alex. Okay, nice to see you in such large numbers tonight. Thanks for coming. My name is Zacharias Fisches. I'm a machine learning engineer at VARA, and I think the slides haven't updated yet. I'll just reload quickly. Here we go. Now it says VARA. Yeah, we used to be the only purple company from Merantix, but now I think as Momentum is also carries purple. So I'm wearing company colors tonight. I'm very pleased to present to you my part of the NeurIPS 2022 highlights. It was the first time I was in person at NeurIPS. And so one of the main differences when you go in person besides meeting friends is all the free lunches. And we had an internal competition who could get more free lunches, but I won't reveal who was the winner. And so tonight I try to bring another kind of free lunch to you guys, because I feel like many papers work on very interesting ideas, but if you work in an applied setting, data is often not so easy to come by. And so squeezing the maximum from the data you have is always interesting. And we work on breast cancer, AI. And so naturally, cancer data is also quite rare and not so easy to come by. So I'm presenting this paper called The Unreasonable Effectiveness of Fully Connected Layers for Low Data Regimes, which I found pretty interesting. And the idea is very simple. The authors augment a convolutional neural network with fully connected layers on top. So they just add fully connected layers in between the CNN stack and the head. And they show that this is very good for low data regimes. And this paper was accepted at the main conference. So apparently this was not so well known to the NeurIPS community. But for us, it's interesting because we arrived at the similar solution for our problem to machine learning engineer descent over the years. I'll quickly go to the module they add. They call it a feature refiner. You just take the activations of the last layer before the classification layer of your network. You add the fully connected layer that reduces the dimension to something smaller, and then layer norm fully connected, ReLU fully connected layer norm. And then on top, you apply the same fully connected layer and softmax that you'd usually do. And you use that to get your predictions. And now it turns out if you do this on Cypher 10 or Cypher 100 with the small ResNet, the less data you use, the more performance improvement this gives to you. So Cypher 10 and 100 have 50,000 training samples, and here they use 1,000 to 10,000 samples. And if you're in the low data regime, this improves your performance a lot. Okay. Now let's understand sort of this a little bit better. I suppose when you want to publish a paper like that, you really need to add some flesh around such a finding. And so we do the same thing on different data sets. We train with the very standard setup of SGD with momentum plus weight decay. And okay, the authors for the harder Caltech data set, the authors don't reduce in their feature refiner to 64 units, but instead to 256. So a little bit of tuning might be required. And they also initialize from ImageNet pre-trained weights, but that's just to give you an idea how they can reach 76% accuracy with so few samples. So this works across a couple of data sets at least, but it also works across a couple of architectures here, ResNet 34, ResNet 18, DenseNet, and EfficientNets, all kind of look the same. And then in the paper is pretty thorough actually from Munich, TU Munich. They also compare to some modern stuff that you might like better than convolutional networks like MLP mixers or visual transformers. They compare how this works if you do knowledge distillation, how this compares if you do self-supervised learning, all in the small data regime. They also show that this works in combination with semi-supervised learning. They also show that this works with Caltech, with the Caltech dataset without pre-training. And the only thing where it doesn't work so well is if you check the robustness of the results under corrupted images in your evaluation set, where it turns out that if the corruptions are very strong, then not having this extra feature refiner on top of your network is better. And I would say that could be just because simple models are better maybe in this situation. So one question that naturally arises is there anything special about this feature refiner? And there's an ablation that says what happens if instead of the feature refiner, we do something that's less than this. For example, just a single fully connected layer in between the classification layer and the features, and even without activations. So in my mind, this is just a linear layer before a linear layer, so that shouldn't give you much in practice, but in fact it does. And then if they add the second one, and they can reduce they introduce this sort of bottleneck dimensionality, or they add layer norm and they recover the full thing, and you see that all of their things sort of add a little bit, but adding something is better is already most of the benefit. Another question you would probably have is, how is this possible? Is this just because we add a ton of parameters on maybe increase the expressivity of our model? And so to test this, they essentially take away the feature refiner, use the features that the backbone learned under linear probing, and show that that this is actually gives you similar results. And here, the only thing that they contribute to, in addition to the system, is they formulate this in a kind of end-to-end online fashion, where they simultaneously give you a prediction in the original model, which is green, and in the feature refined model, which is blue, and they train on a sum of two losses from both things, and they make sure that the backbone is actually only trained through the feature refiner by putting this gradient stop operation in between the original classification layer and the features. So this thing, what it gives you is that you learn features that are somehow trained through the feature refiner, and you evaluate them in the end and in the original setup. And with this, they still find that it performs essentially the same as directly predicting through the feature refiner. So something about the actual features your network learns is better when you add fully connected layers in a low data regime on top of your network. Interesting, if you go back to what they call an old-fashioned model here, a VGG11, where fully connected layers are already on top, then this benefit goes away. And if you do it with modern architectures, which supposedly didn't need fully connected layers anymore, then you get all the benefits. And if that's not free lunch, then I don't know what is. I'm happy to take 2 questions now and then move on. I'll definitely speed up a little bit for the next part to not stand in between you and the semifinals any longer. Yeah.
Thanks. So just to clarify, like they train from scratch every time? Yeah,
they train from scratch, except on Caltech, where they transfer weights from image and pre-training.
And do you have like an intuition?
So the feature refiner is sort of part of the architecture. They train it as a whole.
So do you have intuition, like why it helps? Like what's, it's like sounds pretty random, but you said you came up with a similar thing. So I thought like you didn't randomly come up with it.
So we came up with it because if you use a BGG, you get these, you usually have these fully connected layers. If you try to remove them, it doesn't work so well anymore.
But no intuition?
Not really, yeah.
Okay, thanks.
So one thing that the authors said when I asked them the same question in front of the poster, they said that, which is maybe also trivially the case, that your gradient signal is somehow different. If you need to learn linearly separable features, it might be sort of a constraint on the learning dynamics compared to if your convolutional features don't need to be linearly separable, but sort of can be a bit more complex, because the feature refiner will sort of take care of it. So the surprise is a little bit that in the end, they still showed that the features that you end up with at the end of training are linearly separable to give you the same accuracy, right? So that's quite interesting. Thank you for this question. The other thing I always like to follow a little bit is what happens to SAM. SAM is short for Sharpness-Aware minimization. I went to the posters and collected a couple of follow-up papers that I found interesting. I'll give you the references here. Not like this, but like this. There was one that's called "When Do Flat Minima Optimizers Work?" Another one, make sharpness-aware minimization stronger, a sparsified perturbation approach, and also sharpness-aware training for free. I'll definitely speed up, so don't worry. Let's say the TLDR is the first one is looking at SAM plus stochastic weight averaging separately and in combination. The second one sort of says SAM is too expensive. What if we make it sparse by doing the perturbation only on some of the weights? And the third one says SAM is also too expensive. What if we replace the perturbation by instead monitoring something about the loss trajectory, with the idea that a large difference in loss would somehow mean that we are in a not flat region of our loss landscape, and a small trajectory loss difference would indicate a flat region, which is what sharpness-aware minimization is always going for. If you've been following our reading group for some time, you maybe remember this slide. So what SAM does is you're in your loss landscape, in your loss manifold space at a time t. So you're at WT. Now you can, instead of making a gradient update in the direction of lambda of your loss, nabla of your loss, instead, which would be here, instead you perturb your weights by going in the opposite direction, then you'll end up here. You calculate the gradients again, and then which would give you this kind of update. And then you apply that update to your original parameters. So if you kept track, you need to calculate your gradient twice and update your parameters also twice, because once in order to go to the perturb point, and secondly to then apply the gradient update, and then you end up at your next step under SAM. Somehow it's better in certain situations, but the cost is everything is twice as expensive given all the weights that are trainable. So if you're in a situation where, for example, you transfer a frozen backbone onto underneath like a small trainable head, then using SAM could be very compute efficient for the performance that it could add to your systems. The paper then shows that the error is reduced on basically all the data sets that they show, and they visualize this and claim that we end up in areas of flatter loss curvature. So when do flat minima optimizers work, visualizes these the same loss landscape under some linear interpolations, and they compare stochastic weight averaging to SAM. I'll just show some highlights. So they show that SAM gives you flat areas in the loss landscape of your training. Here it's a bit unclear why this is flat, because X is the point you end up when you SAM, and the dot is where you end up using vanilla SGD, and they interpolate between the weights of these two solutions linearly, so obviously from the same initialization. And then you see under looking at the Hessian or something, you can still see that these areas here are pretty flat, but they're at the edge of some things that are not so flat. While stochastic weight averaging, the two solutions are also in somewhat flat areas, not quite as flat, but they somehow end up in similar basins of the loss landscape. Okay, so here you're end up with a really different solution. Here you're sort of are in the same area just in a little bit of a flatter part if you use stochastic weight averaging. They show then in the end that if you combine stochastic weight averaging and SAM, meaning you optimize with SAM, but still run the exponential moving average of your final few checkpoints as a stochastic weight average, then you, under some conditions, get the benefit of both. I think what made this paper interesting is that they evaluate quite carefully, and people sort of add a little bit to our understanding of what SAM does. So the second paper, make sharpness-aware minimization stronger, a sparsified perturbation approach. They find that perturbing all the weights in your optimization in order to determine your gradients that you then apply to the original weights is suboptimal, and also it increases the computation. And so instead they derive some rules for how to sparsify the perturbation. And you can think about the sparsification as taking the original perturbation and then multiplying with the binary mask, which is 0 in most places and non-zero and 1 in others. And then you end up with your final perturbation. They show that this works on C/10^100 image at 1K, and can even be better than the original SAM, which they motivate in a bit more detail in the paper. For example, there's a paper from 2016 apparently showing that merely about 5% of the parameter space is sharp in the loss landscape, but the rest is flat, meaning you kind of are only interested in 5% of your parameters and the rest doesn't really matter, and maybe you also shouldn't perturb it. They also measure what is the difference between the gradients that you get under normal SGD at each step versus under SAM, and you can take like a relative difference ratio, and you see that most weights have a negative relative difference ratio. So this takes the logarithm, and they indicate that this indicates that most gradients are the same, pretty much the same, and kind of gives you an intuition that you want to focus on the ones where it's important. Now, how do we get to this binary mask? It's a little bit more involved. They actually suggest 2 different ways of doing it, and then also gives some theoretical results. Here, I only noted the first one where they compute some kind of empirical Fisher criterion. And they only do that once every few epochs because it's quite expensive and they need to sample from their data set. So it's like a forward pass to a part of your data set in order to determine this. When you have the vector of the empirical Fisher criterion, then you take the one, oops, this is something missing now, it's just hidden for me. Then you just select the top K of those to be 1 in your sparse mask, and every other parameter that carries less information to be 0. If you have a very modern hardware where sparse optimization is efficient, you can reduce the number of flops from 2x to something like 1.6 or 1.3x, and still sort of get to the same performance level, more or less. And that's the same thing in a more visual way. So if your sparsity is at 50%, you're pretty good. If your sparsity is at 99%, you lose a little bit more, but it can still can still be pretty good. Sharpness-Aware training for free takes a different approach. They say we want to replace the whole computation of another gradient and gradient update in order to determine our perturbation, which I feel is a very interesting idea. And the intuition is that we want to avoid sudden drops in the loss, because that could mean that you're sort of around sharp local minima. And so if you can measure sort of the drops in your loss with some kind of metric, and you can optimize that metric as a regularizer to your network, then you would end up in areas with a solution that is in a flat area of the loss landscape. So this is the intuition that your trajectory loss that they define is somehow lower when you're doing gradient update steps in around the flat local minimum than around the sharp local minimum. And they show that their method is much faster than the original SAM, which is here in orange, and their sharpness-aware minimization for free, SAF, is here up and to the right, so on the speed accuracy curve. And I'll leave the rest to homework for you guys. Thank you so much. So yeah, that concludes our NeurIPS highlights 22. I'm happy to take maybe a little more questions, right?
Yeah, I think if there are questions regarding the last part, feel free to ask. One question from my side, I took away, like one of my main takeaways from your talk was that only 5% of the loss landscape are actually sharp. Can you like maybe explain a little bit like how sharpness is usually measured and like what sharp actually means? So is it just like the Hessian, or is it like the variance of gradients, or like?
So I think in I'm not sure, but I think in their definition of the 2016 reference, they say if I perturb the parameter, how much does my loss change? I think that's it. But in generally speaking, we're talking about the Hessian.
Thank you.
Like the point where I'm not 100% sure is when we visualize this in 2D or 3D. But yeah.
How do they get the fancy visualizations?
Yeah, I just haven't looked into it.
Magic. Cool. I think then we're through. Thank you so much to our speakers once again. It's been a pleasure to have you all. Also, thank you so much to the online crowd for sticking around. And just wanted to say that this is really a space to connect. So please feel free to stick around and mingle a little bit and get to know the Berlin machine learning community. And if you're ever interested in speaking here at this event yourself, come and speak to me. I think, we're really an open stage for any machine learning research topics. If you want to present a paper or some topic, come speak to me. Thank you so much, and see you next time.
Thank you.